Good morning friends. In today's lecture we are going to see some numericals based on the double reinforced section. In our previous lecture we have seen what is the necessity of double reinforced section, what is mean by double reinforced section, and how to design a double reinforced section. Okay, today we will solve some numericals which are generally asked in the university examination. So we will practice some numericals. So first I will read the numerical for you. Please note it down and then we will solve. Okay. An reinforced concrete beam 200 mm by 300 mm effective is constructed with concrete M20 and steel Fe415. Find the steel required if the factored moment on beam is 74 kN meter. Assume D is equal to 30 mm. D dash means effective cover is equal to 30 mm. Okay, so depth of beam is given, width of beam is given, factored moment is given, and grade of steel and concrete both given. Okay, so we have to design, we have to calculate the reinforcement required for the given beam. Okay, so we will start with the analysis. So first of all, see, the width of beam B is given, it is 200 mm. Then depth of beam is also given 300 mm. Then D dash effective cover is given 30 mm. Then factored bending moment is given MD, which is equal to 74 into 10 raised to 6 Newton m. Or you can say 74 kilonewton meter. Both the values are same. Okay. Now, first we will calculate the design constant. What is XU max or XU limit we say. Now, as the grade of steel is Fe415 grade, so XU max will be calculated as 0.48 into D, which is given 300. So 0.48 into 300, it gives 143.7. Okay, so XU max is given. Then next we will calculate MU limit. So what is MU limit? MU limit is the limiting moment of resistance which can be resisted by the beam, and it is, we have derived this equation for MU limit for different grades of steel. If the grade of steel is Fe250, then the equation will be different, means only the constant will be different, otherwise all the remaining terms will remain same. Okay, so for grade Fe415, our grade is Fe415, Fe415 and M20. So Fe415 grade for Fe415 grade MU limit is equal to 0.138 FCK BD square. If you go through your notes in which this value of equation is given, okay, we have derived this equation. If you refer the notes of chapter number 1, you can see this. Okay, so 0.138 FCK is now 20, B is 200, and D is 300 square. Okay, so this is equal to 49.68 kilonewton. See, in exam many times they will not mention whether you have to design a double reinforced section or a single reinforced section. They will ask you to find out the reinforcement required for this beam. So now the statement is calculate the reinforcement required for the beam, and you don't know whether it is a single reinforced or double reinforced. Okay, so this value will give you the identification of the section. Means from this value you can identify whether the section is under a single reinforced or double reinforced. Now you just have to compare this value with the given bending moment or given factored moment. So factored moment is now 74 and limiting moment of resistance is 49.68. If the factored moment is more than limiting value of moment, then then it means you have to design that section as a doubly reinforced section. Okay, so this section you have to design a doubly reinforced section as MD is greater than MU. Okay. Now what is the extra moment for which the extra steel or extra reinforcement, double reinforcement is required? What is that extra bending moment? So it's 74 minus 49. So MD minus MU limit. So MD is 74 minus 49.68. So this will give you the value 24.32 kilometer. Okay. So now you have to calculate the reinforcement. Okay. So reinforcement to resist this bending moment, that is 49.68, and reinforcement to resist is 24.32. Okay. So you have to calculate total reinforcement in two ways. One, reinforcement required to resist this MU limit, and reinforcement required to resist this MD1. Now the reinforcement required to resist this MD1 extra bending moment you have to provide on both sides. That is on tension side also and in compression side also. Because to resist or to develop this type of support, you have to generate extra tension as well as extra compression. And that extra tension and extra compression both will be provided by the additional steel on compression side and additional steel on tension side. Okay. So first we will calculate this one and then we will calculate the reinforcement required to resist this additional factor bending moment. Okay. So let us start. So first calculation of AST1 which is required to resist this bending moment. So this can be calculated just by applying the principles of a single reinforced section. Okay, you just have to apply the reinforcement. How you are going to calculate reinforcement for single reinforced section? Same method, same procedure you have to adopt to calculate this AST1. Okay, so you can use the bit limit equation or you can use compression is equal to tension equation. Okay, both the equation can be applied here. Whichever is convenient to you, you can apply. For bit limit equation, you must know the values of bit limit for different grades of steel and concrete. So many times it may be confusing. So in that case, it will be better if we use this expression compression is equal to tension. So for compression, we know the formula 0.36 FCK B into XU. Now for here we have to take XU max because we are calculating this AST1 for this MU limit. So here is MU limit, so definitely here will be XU limit. Okay, and tension 0.87 Fy into AST1. I am going to refer this as AST1. AST1 reinforcement 1. Because here you have to calculate AST2 and ASC. So AST1 is equal to 0.36 FCK B XU max whole divided by 0.87 F1. So 0.36 FCK is 20, B is 200, XU max we have calculated as 143.7 divided by 0.87. Fy is 415. If we calculate this, we will get 576 mm. We get 576 mm. So we have calculated AST1. Now AST2, how will you calculate AST2 and ASC? Now for the calculation of AST2 and ASC, we have equations, that is additional tension MD1, sorry, we have referred to this as MD1. So MD1 can be developed as additional compression into lever arm. So now where the additional compression is generated, see, additional compression will be generated by this AST, by this ASC and this AST2. These both will develop the additional tension and compression. And the lever arm between these two, this is CU2 and TU2. Lever arm means its effective depth minus this D dash. D minus D dash. We have developed this equation. Okay? Now, additional compression we have to calculate. So, formula for additional compression is ASC into bracket FSC minus FCC into lever arm is D minus D dash. Where FCC we know that 0.446 FCK, and this FSC value, that is compression speed, compression stress in steel, we have to derive from the interpolation of D dash by D ratio. I have given the chart in my previous lecture from which you can calculate the FSC value. Okay. So now for that you should know what is the D dash by D ratio. So now one ratio for D dash by D is 300 divided by 30 divided by 300. So it gives 0.1. And for 0.1 value of for D dash by D 0.1 and FP415, FSC will be equal to 353. FSC will be equal to 353. Okay. So now just substitute this value and the 0.446 FCK will be 8.9 Newton per mm². D is 300, D dash is 30. Just substitute all the terms and this MD1 is 24.32. If you substitute all the terms, 24.32 is equal to AC. We have to calculate. Then FSC is known to us. What is FSC? 353 minus 8.92. D dash is 300 minus 30. So ASC is 261.78. So we have calculated ASC now. Okay. So next AST for AST2. So this is ASC. Now we have to calculate AST2. So again, same MT1 now tension to lever arm, additional tension to lever arm. Now additional tension will be AST2 into 0.87 F1 into D minus D dash. So just substitute all the values. Again 24.32. You have to multiply this into 10⁶ here also. Okay. So AST2 we have to calculate 0.87 Fy is 415, D is 300 minus D dash is 30. If you solve this, you will get AST2 is equal to 249.75 Newton. It's mm². So they asked to calculate the reinforcement. We have calculated the reinforcement ASC, AST2 and AST1. Okay. So AST1 is the tension reinforcement you have to provide at the bottom, and ASC is the compression reinforcement you have to provide at the bottom. So total reinforcement at the bottom will be equal to AST is equal to ASP1 plus ASP2. We have calculated ASP1 as a 576. So 576 plus this 249.75 will get the value 825. 275. Okay. So total reinforcement at the bottom 825.475 and total reinforcement at the top 261.78. Okay. So this is how we can calculate the reinforcement required for the double reinforced section on tension side as well as on compression side. Okay. In previous lecture we have seen some numericals. In today's lecture also we have seen numericals on the double reinforced section. So in next lecture we will move towards the next topic, that is T and LD. Thank you.